Now, in this section, we are going to continue with understanding how this so-called chemiosmosis occurs and how this proton movement is happening between the lumen of the thylakoid and the stroma via the thylakoid membrane. So, what we are categorically talking about is, let us say this is the stromal space, right? So, in the stromal space, I am having my thylakoid, right? And my thylakoid contains a surface. Now, this is my thylakoid membrane. This is my thylakoid membrane, which I am representing in this bilayer. It's a bilipid layer, right? Now, on this thylakoid membrane, I will be having these light harvesting complexes, the LHCs and various electron carriers that we've already seen in the light reactions and in the entire electron transport system also. Correct? Now, what happens is, as we have discussed, there will be this movement of protons from the stroma into the lumen. So what here is this space here, this empty space here, this is the lumen of thylakoid, right? So from stroma into lumen, and again from lumen into stroma, there will be this movement of protons which is happening through the, because of the chemiosmosis, again the concentration difference, and for that movement you need specifically a particular proton channel, which is the ATP synthetase. So we are going to understand how that protons are accumulating and how they are moving and why it is resulting in the formation of that many amount of ATP and that many amount of NADPH. Okay, now what I'm going to do is I'm going to remove this diagram from here, from this position, and then we'll continue. Okay, so now everything begins with the non-cyclic phosphorylation when sunlight of 680 nanometers lands on the reaction center of P680. Correct? And as a result, there will be excitation of electrons. Now, how many electrons? We have seen that a pair of electrons, they get excited. So this pair of electrons, what happens is they move from the P680 to plastoquinone. Okay, so plastoquinone now receives 2 electrons. Okay, now plastoquinone will, when it is reducing electrons, it will also receive protons. Where it will receive the protons from? The protons it will be receiving from the stroma. How many? For every 1 electron, it takes 2 protons. So here, because you are having 2 protons, it will take, sorry, 2 electrons, it will take 4 protons. So it is also going to take 4 protons from the stroma, and this is going to become into plastoquinol, the reduced form. Done. Now, the 2 electrons have to now pass from plastoquinone to cytochrome B6F. Okay, and for that, the plastoquinol has to release the electrons. So when it is releasing the electrons, it is going back into its oxidized form of plastoquinol, so that the 2 electrons, they are entering into the plastocyanin. They are entering in the plastocyanin. Then if the electrons are getting released, even the protons also have to be released. So where will the protons go? The protons will go into the lumen of thylakoid. They will go into the lumen of thylakoid. Okay, so that happened here. So let me just remove this little equation from downstairs so that I can add the protons moving into the lumen of thylakoid. Just a second. So how many they have come? They have come for here 4 protons. Okay, now this 2 electrons, it finally passes from cytochrome B6F to plastocyanin PC, which the copper containing one, hence the blue color. And from there it enters into the reaction center of P700 in the ground state. That is that much. Now, when the P700 receives light of 700 nanometers, it also releases 2 electrons. These 2 electrons from T700 go to the FNR complex. In the FNR complex, what it is going to do, its main objective of going into the FNR complex is to carry out the reduction of NADP into NADPH. Now, for that to happen, it cannot just have 2 electrons, it needs protons. So, where are the protons coming from? They are coming from the stroma. How many protons? It is bringing true protons. Okay, so 2 electrons and 2 protons, they enter into the FNR complex. Where by using NADP reductase. What is FNR? It is ferredoxin NADP reductase complex, right? So what they're going to do, they're going to create a situation where the NAD is converted into NADPH. Now, if you just look at this equation in this current scenario, you will see that the stroma is now deficient by 6 protons. Correct? 4 it has given to the lumen and 2 it has given to NADPH. So, it is deficient by 6 protons. The lumen of thylakoid contains 4 protons already. But the difference is not that much. You're not having that much difference to create a osmotic movement. Okay, but you have that difference. If you look at it 4, 6, ma'am, there isn't much difference, right? No, actually there is a little tiny thing that we did not mention. What is that little tiny thing? You're going to see here. Now, as I was discussing, I've told you that there is something called as water splitting. Remember, splitting of water, where we know that one water molecule, okay, it splits. What is it going to split? I hope I'm going to pause it for a second. I expect all of you to do it and write the equation. Hope all of you were able to recollect the equation. So I'm going to write it here. So it releases 2 protons, 2 electrons and half oxygen molecule. Correct. The electrons enter into the PS reaction center, whereas the protons, they will remain in the lumen. Now if you do the calculation, the lumen of thylakoid is rich with 6 protons. Okay, 2 here and 4 here, whereas stroma is deficient by 6 protons. So now what happened? There is a concentration gradient that has been established. Okay, so just a second, let me just change this NADPH position from here because it will become difficult for me to show. Yeah, just a second. Yeah. NAD will be converted into NADPH. Now, because there is a concentration difference that has been established between the protons of the lumen and the stroma, the protons will move from their higher concentration region, that is lumen of thylakoid, to the lower concentration region. Okay, so they will move from the lumen to the stroma by using the ATP synthetase. So how many they'll move? They will move 3 protons at a time, like this. Okay, when these 3 protons are moving, for each of the 3 protons, one ADP molecule is converted to ATP. Understood? So, now how many protons are there moving? 6 protons have to move. So, how many ATP molecules it will form? It will form 2 ATP. And how many NADH molecules have it already formed? It has formed 1 NADPH molecule. Right? So, one Z scheme of electron transport produces 2 ATP and NADPH in this mechanism. Okay, so this is the actual proton movement that is happening within the walls of the thylakoid membrane.